Hi everyone, welcome to our week 7 live stream. Since it's 12, I'm gonna go ahead and get started. If you have the worksheet with you, please feel free to pull it out and follow along with me. All right, this week we're gonna be looking at behavioral and population ecology, and first we're gonna be focusing on the behavior aspect of it. So the first part of this worksheet is mostly going to be figuring out how we can ask the right type of question in order to figure out the exact information that we're looking for. So here's the premise. Some plant species, for example, many orchids, rely on a single species of insect for pollination. If the insect species dies out, so will the plant. In parts A through C, refer only to the behavior of the insect species. Okay, so the background information that we have now is that certain types of plants rely on only one species for pollination, and it's also known that if that specific species dies, then the plant dies along with them as well. So we're going to be looking at it from the perspective of the insect and trying to figure out how we can get these information. So the first one is, what kind of questions would you need to ask to determine proximate cause of this behavior? So, can anyone tell me what proximate causes are versus ultimate causes? All right, I see a chat. It says genetic causes and ultimate causes uh, would be like evolutionary causes. Yeah, so I kind of see that with the ultimate causes. What you've described reminds me of ultimate causes because we look at that in terms of evolution, like how and why the behavior came to be. And then the proximate cause would be what mechanisms enable that organisms to be able to exhibit that behavior. So the main thing I would remember is ultimate, think of in terms of evolution, and proximate, think of in terms of mechanisms that allow for an animal to behave in a certain way. All right, so the first question, or question A, is asking us about proximate cause. So we need to look at what mechanisms enables the organism to behave that way. And we're looking at it in terms of the insect species. So some questions we can ask are, what are the specific characteristics of the orchid and the insects? This will help us figure out some of the mechanisms. Another one we can have is, um, what about their morphology that only allows the insects to be limited to one flower? So this is kind of asking, why is there only one insect to one plant? And that would also be a proximate cause because it's talking about their mechanisms and their ability to do so. Another questions that you can ask is there specific insect species that are unable to pollinate other flowers? So this is kind of a similar question, but looking at, are they unable to? And then other things you can look at are color pattern, fragrance, type of nectar, everything else that might draw the insect to only this type of orchid. All right, so part B, now we're looking at the ultimate cause, and this is more about evolution. So a question we can ask here is, why would this type of symbiotic relationship between orchid and pollinator evolve? So that would be the ultimate cause of why we see this behavior. Or the answer to this question would let us know why this type of behavior exists. All right, and then C is asking, what kind of experiments or investigation would you propose to answer at least one of the question in part A and part B? So there's multiple correct answers here, but for an example, I'll do what factors draw the insects to the flower. So in order to test this question, we would need to test each factor separately. That's very important. So we can avoid having the confusion of which variable is actually causing the change. So we need to test each factor separately. How we can do this is we can place individual insects in a test chamber, and then we can test for nectar preference. So we might have like one plant exhibiting one type of nectar, another one with another type of nectar, and then we can see which one the insect actually prefers. So that way we can see, okay, is it the nectar that it prefers? And if so, like what type of nectar that it prefers. Uh, we could also observe their insects like response to the different types of nectar, whether they only go to one plant and how often they go to that nectar. Is it like every 5 minutes, every 1 minute? So that would let you know how much they prefer the nectar. And then we could also do the fragrance. And for fragrance, we would need to get rid of the nectar because we need to test each variable separately. So we would get rid of the nectar component part, and then we would test for fragrance. So have different types of fragrance, see which one the insect prefers. And we can do that with any other factor that we're trying to test here. So that could be one way to investigate the questions that we proposed above. Any questions so far? All right, not seeing any questions. All right, let's move on to question 2. This is going to be similar to the question that we did, but in a different scenario. The scenario is, many bird species common in the northern United States during spring and summer fly south in the fall to overwinter and feed in Central or South America. In the spring, they return to the northern United States to breed. So, what questions would you need to ask to determine proximate cause of this behavior? Comment says no questions yet and finally made one of these review sessions. That's awesome. Yeah, I'm glad you're able to make it to this time. All right, let's see. Okay, what questions would we need to determine for proximate cause? So one other question we could ask for the proximate cause is how do birds know when to fly north? Because that's the mechanism that they use. So that would be one of the proximate cause of behavior. Um, have a comment that says, can one be what drives the birds to fly north? Let's see. Yeah, I think, yeah, that would definitely be proximate. But if you were to word that question a little differently, if you said, why do the birds fly north? And like, why do they have that behavior? Then that would be your ultimate cause. So yeah, the drives for why the birds fly north would be proximate. So let me write what drives. And then I'm going to do the ultimate cause, like wording that question a little bit differently, and that would be why do birds fly south or north? And then another one for the ultimate would be why would this type of behavior evolve? All right. So similarly, we're going to do like what kind of experiments we could propose to answer. So say we're looking at environmental factors that promote them to fly south. We could test that by looking at the change in day's length on birds' behavior. So for example, we could like put them in like chambers with like artificial environment and like control the amount of light that they get and see if the amount of light that they got affects whether they fly south or not. But yeah, there could be multiple correct answers for these questions. It just depends on what question you pick. All right, any questions so far? All right, let's look at the next question. This one's a little bit long. It says many species of animals engage in complex courtship rituals. Among these species is the bowerbird of Australia. Male bowerbirds construct elaborate structures or bower from twigs, leaves, mutton moss, and decorate them with colorful objects such as berries and shells. The bowers and the dances the male perform are designed to attract female bowers for mating. After mating, the females fly away to build a nest and raise the offspring. The males remain at their bowers and try to attract additional mates. These birds can live up to 17 years. Males are territorial and build their bowers in the same location each year. In studying this behavior, researchers have noted about 25% of females shop around, going from one bower to another before deciding on a mate. The other 75% appears to go directly to a single bower to mate. These behaviors cannot be observed in captivity. Okay, so they just described certain behavior between male and female bowerbirds, and then at the end, they conclude that by saying that these behaviors that they just told us about are not observed in captivity, so they're only observed in the natural environment. So we're going to be asking some questions to figure out why that might be. So one question we could ask to determine the proximate causation could be to ask what characteristics of the environment triggers the bower building response in male, because the question pointed out that it's only observed in nature, not in captivity. So asking a question like that would help us determine the characteristics of the environment. And then for the female proximate cause, we could ask, what about the male's dances that trigger mating response in female? Because they talked about how 25% go from like one male bird to another bird to like scope out, whereas the 75% just chooses one. So we can look at what about the dance that actually attracts the female. Okay, and then for ultimate causations, we could ask, why did this elaborate mating ritual evolve in the first place? What evolutionary history led to the behavior? So from the three questions that we've done, you can notice that for proximate causes, we use characteristics a lot, like what characteristics of something led to this behavior. But then for ultimate cause, we always use the word either develop or evolutionary. So be aware of those keywords that can help you determine between whether it's proximate or ultimate. And also another thing that you can notice is for ultimate, we tend to start with why did something happen, whereas for the proximate, we tend to use what characteristic triggered something else. So what tends to go with proximate and then why tends to go with ultimate usually. So don't use it as like 100% rule, but just like quick things to like focus on if you're like pressed for time. All right, and then similarly for the last question, what kind of experiment we could do to get an answer to some of that question? So So if we're looking at what characteristic of the environment triggers the male burrowers to build, maybe we can study, well, we can't study them in captivity because we know they don't exhibit that behavior. So we would need to study them in their own environment. So maybe we can look at like the days and weeks leading up to the behavior and compare that to like the rest of the year to see if we're able to find a difference. And maybe that difference can give us a clue to what in the environment triggers the male borrowers. Okay, next we're going to be switching our gear to look at population. And before we move on, do you guys have any questions on any of the questions that we've done so far, or how to determine between ultimate versus proximate causes? Okay, I haven't seen any questions so far, but if something comes to you later, feel free to put it in the chat, even if it's from above. All right, so we're going to be looking at how people actually determine population size in the wild. So, to measure population density, well, here they're using chipmunks as a specific example, but this can be done with different organisms. Like, I remember in high school, we did one with bees. Like, you would capture bees and like put a little red dot on them and then release them back again and see if we like captured the same bees. But here they're talking about chipmunks especially, and they want to measure the population density in a specific park. And what they did is they made several quadrants and captured 50 chipmunks, and they put a mark on each of their back with a small dot of red paint, and then they released them back into the nature. And then the next day they captured another 50, and among the 50, they found that only 10 of them were marked. So, using this comparison, like how many they marked versus how many they were able to capture that were marked in the next day, you can use that to estimate how big the population is. So, how many chipmunks might be in that population. And to do that, there's this formula. And here's what they mean. So, the M2 is going to be number of recaptures in second catch divided by total number in second catch. That is equal to, so you're setting up a proportion for a number marked in the first catch divided by the total population. So usually we're trying to find this. So this is usually the unknown. So in this example, the number of recaptured in the second was 10, and then total number in the second capture was 50 because they caught 50 in the second capture, and only 10 of that were marked. So it would be 10 over 50 equal to number marked in the first catch, which was 50 because it says here that they captured 50 chipmunks, and then this is what we don't know. So if we set up the proportion, how it comes out to, it could be 10n equal to 50 times 50, and then you can divide by 10, and then n equals 250 chipmunks. So that's your estimate of how many chipmunks could be in the population. Okay, did that make sense to everyone? All right, so we're gonna be looking at more questions. So later we discover that you've sampled the one area in the park that was most favored by the chipmunks. So what effect would this have on our estimate? So this new thing tells us that the area we picked is preferred by chipmunks way more than like any other area. So how would this affect our discovery? Would our estimate of the population would be larger than it actually is, or would it be smaller? I have a comment that says larger, and that is exactly right. So if we picked a part where chipmunks just love to come, then we're going to end up capturing more than we would have in a different part of the location. So we tend to get that, like a sample tends to be like higher in that specific location. So our population estimate would tend to be larger than if we had sampled more parks, which is why it's usually like a good practice to test more than one location when we're doing this, so we have more samples to compare and we don't have certain biases like this. So this would cause us to overestimate the population. All right, the next one is, I found this one a little funny. So you later discover that the chipmunks were licking the marks off of each other's backs. So how this would affect is that we would capture some chipmunks that were counted as unmarked that could have had their marks licked off. So essentially they're just getting rid of our marks. And as a result, our estimate of the population would also be higher because we're thinking that these are chipmunks that we hadn't caught before when in fact we did catch them before. We just lost our measuring tool, which was the mark. So in this situation as well, this would result in our guess to be higher. So our estimate would be higher. Okay, and then another one of these scenarios is that we discover the marked chipmunks are easier to see and therefore more susceptible to predation. So this is saying that marked chipmunks are more likely to die off and like not return in our sample. So this would indicate that we will capture fewer marked chipmunks than we should have, just because they're not in the population anymore, they're dead. So the probability of catching marked chipmunks reduces by a lot. Therefore, the population size that we calculate will also be reduced by a lot. So it's proportionately going down. So it's not that we overestimated or underestimated, just because like as the red chipmunks disappear, our estimate like decreases by the same amount. So our proportions are still the same, but it's just that we're not able to accurately quantify the population. All right, and then finally, what modifications could you make to make the sampling program more accurate? So, what do you guys think would make this experiment more accurate? Thinking about what we've talked about and like what you previously know about accuracy. All right, I can start off with one. So one thing that came to my mind was just, oh, let's see, we have an answer. So use tags that they don't like to lick and also put the tags where the predators can't see them. Yes, that is a great answer. I really like that. So using mark systems that can't be detected by predators. And this would avoid the third scenario that we were talking about in the question. And another thing that we could do is sample more than one parts. Another thing is put up a sampling system that can't easily be licked off of the squirrel or chipmunk. So marking system that can't be easily removed. All right, next we're going to be shifting gears a little bit. So instead of looking at population estimate, we're going to be looking at um, like different levels of density. So like and how they change over time based on mortality rate. So let's see. The following table provides the number of deaths per acre per year resulting from the operation of two different agents of mortality in populations of grasshoppers at different density levels. Fill in the mortality rates of A and B in this table. So basically what we're going to be doing, we're just going to be taking percentages. So for agent A, here we have 4, here we have 100. So we're going to be doing 4 over 100 for agent A. So 4 divided by 100. And then here would be 0 over 100. So this will be 4%, this will be 0%. And if we continue the same logic, this would also be 4%. This would also be 4%. This would also be 4%. But agent B starts increasing more. So we see 2.5% here, 5%, And then let's see, this would be 50% here. So that's how we got the mortality rate, just taking a simple percentages from your population density. So just make sure that this part is population density and that this part is death per year. So if you have those two things, then you can calculate your mortality rate. And then let's see, a graphical representation of it could look something like this. So we saw that agent A stayed the same at 4%. So agent A stayed the same at 4%, whereas agent B increased. So that's what we see here. So agent A just, these are really thick lines. Let's see. Okay, so agent A we see stays in a straight line. And then agent B, we start off at 0, goes up, and then just drastically goes up. And we also saw those in our numbers. So we see it started with 0, went up a little bit, went up by a half, and then from 5 it shot up all the way to 50%. And that's what we see in the graph here. And then for our few questions. Okay, so which two of the agents of mortality, A or B, is operating in a density independent manner? So what do you guys think? Do you think A is acting in an independent manner or B is acting in an independent manner? And here's the graph again, this might help. Common says A, and that is right, because here we see no matter what happens to the population density, whether it's 100 or 100,000, it just stays at 4%, which means it doesn't really care about how big the population density is. So so we say that it's acting in an independent manner, whereas B, we see that it depends on the density. So at 100 it's 0, but then at 100,000 it's at 50%. So it does care about how dense a population is and how it affects a population that's more dense. Okay, and then which one do you guys think acts as a factor stabilizing the size of grasshopper population? So which mortality agent do you think tends to stabilize a population? Here's the graph again in case that's helpful. I'm seeing agent A, but it would actually be agent B. I can see why you think it's A because A is like constant over time. We might think that it tends to stabilize the population, but it's actually B because say you want a population to stay at 50 individuals, like you don't want it to go more, you don't want it to go less. If agent A was acting, then agent A is only going to remove 4 people every time. So even if the population's at 50 or if it's at 150, agent A is only going to remove 4% of that, which means that as your population increases, it's not being stabilized, it's still increasing because Agent A is removing the same amount as it would even if the population was 5. But then for factor B, it's proportionally taking away people. So at a lower number, it's taking away lower people. At a higher number, it's taking away higher people, which means it's helping the population be stable around a similar value. Yeah, I hope that makes sense. If it didn't, let me know. Yeah, another way you could think about it is like no matter how large the population is, A is only going to remove 4%, which means as the population gets big, it's not going to stabilize because it's going to let the population get big. Okay, let's see. Comment says so B has the most drastic effect on the population, so it has more influence on stabilization. Yeah, and I would also think about it in terms of like proportion. So it does have the drastic effect on population, but on the other hand, you also see that as a population increases, the amount that B kills the individual also increases. And then it goes the other way. Like if a population is smaller, then B kills smaller people. So it has a linear proportion to it, whereas A is just stable. It just doesn't care whether it's big or small. Whereas B kind of adjusts to whether it's big or small. All right, that was our last question for today's worksheet. Any other questions that you guys have? All right, I'm gonna put the extra credit link in the chat and make sure to fill it out. Thank you, and yeah, you too have a great weekend. All right, everyone, I hope you've gotten a chance to open the link. I'm gonna end the live stream right now. Thank you for coming and being interactive through the chat, and I'll see you guys next week. Bye. Hi everyone, welcome to the live stream today. I'm just getting some things ready and then we'll get started. All right, so today's video live stream is going to be similar to other ones that we've done, the one from last week. So it's still going to be about population and community ecology, but we're just going to be looking at it from a different perspective. And we're going to be looking more into like the mathematical parts of it as well. All right, so if you have this worksheet, please go ahead and pull it out. So there's going to be a lot of numbers and words in this worksheet. So if anything gets confusing, please feel free to let me know in the chat. All right, so let's look at the first study. So researchers has recently discovered 3 species of parasites that infect developing salamanders. He suspects that one or more of the species causes fatalities during development. To test the hypothesis, the research set up a series of experiments. In each experiment, he varies the density of the salamander population. He infects 2% of each population to start off the experiment and measures the mortality rate after 4 weeks. To establish a baseline mortality rate, he sets up a control experiment that differs only in that no parasite was introduced at any density. So the data below is basically giving us the density and the death rate. So he had 4 different groups, and then he also had a control group where he didn't introduce any parasite at all. And another way that it might be helpful is to look at the graph. The table has a lot of numbers, but here we can see that this is A, this is B, and C and D. So we see in C nothing really happened, but in A, the mortality rate shot up really high as the density went up, and then here it kind of fluctuated. So for me, like I'm a visual learner, so it really helps me to look at graphs rather than charts. So we'll be using this to answer the next few questions. So given the data presented in the graph, indicate whether each of the parasite species is acting density dependent or density independent. So can anyone tell me if A is density dependent or independent? So density A, since it varies based on population, so we see that as the density increases, the mortality rate goes up. So we know there's some correlation to that. So we can call parasite A density dependent. And I usually check that by seeing whether increasing the density actually affects the y-axis. So if increasing density has no effect, then that means it's acting in an independent way, which is what we see in some of them. But so like for example, B, for B, we see that it kind of stays consistent, even though it's the control group. So B produces greater mortality rate than the control. So D's are controlled, but then the mortality rate for B is higher. And it might be tempting to say that's dependent, but we can notice that even at 20 or 320, it's kind of around the same rate. So the mortality is around the same rate. So we know that this is going to be density independent because it doesn't really care whether density increases or not. Then for C, it doesn't act in a density dependent fashion. So C is right here. It kind of goes down, goes up, goes down, and then flattens. but we don't see a specific trend. So for A, we see that as density increases, the mortality rate increases. But with C, it's kind of random. So we can also safely say that it is density independent. We can also call this like not density dependent. And then parasite D is the control. And this shows the same mortality rate regardless of population density, so this could also be not density dependent. All right, do you guys have any questions about that so far? All right, let's move on. So after looking at the data for parasite A and B, develop an argument to indicate which is more likely to cause extinction of the salamander population. So for this question, I like to think about what parasite drastically affects the population. So if we go back to this part, we see that parasite A, if it's highly dense, it almost takes down like 85% of its population. And then for B, it produces greater mortality rate than the control. However, it's kind of consistent throughout the population. And so again, we're going to use like the data that we did in the last question. But we're going to see which one can't rebound. So for example, A might be tempting. Like first I thought A would be the parasite that would wipe down a population, but B also has a really high mortality rate. But the difference between A and B is that A cares if the population's high. So say the population is affected by parasite A, then once the population reaches 20 or 10, then the population is not as affected, which means the population isn't likely to become extinct because there's still the surviving 10 which can reproduce. However, for parasite B, even if you reach 20 or 10 or even 5 individuals, it's still going to have a mortality rate of 85%. So that's going to continue killing people even when the population becomes very, very small. So therefore, parasite B is going to make it harder for the population to rebound and more likely to cause extinction in the population. Does that logic make sense? All right, next we're going to be looking at population models that we can use. So here I'm just going to be defining each term. So population can be modeled using this equation right here, typically. And I'm just going to be defining the variables. So we know that the triangles are going to be change. So the change next to the n represents change in number of individuals. And then the other triangle, I'm just going to number this because sometimes it can get confusing like what triangle I'm talking about. So let's say this is triangle 1, this is triangle 2, and then this is 1 and this is 2. All right, and then the second one is time interval during the change. All right, and then R, the little r, is going to be per capita population growth rate. And then finally, the N is going to be the initial number of population, which is the number that we started with before we're going to be doing the models. All right, does anyone know if this equation is for an exponential model or a logarithmic model? All right, I'll just tell you guys the answer. So this equation, remember that it's for an exponential model. And this is how it usually looks. It's gonna look like this. All right, and it looks like the words are a little cut out here, so this part is supposed to be right here. So the questions would say population growth may also be represented by the model this. Oh, also I forgot to mention what assumptions are made about this model is that we're going to assume that there's unlimited space and resources. The reason why we need to make this assumption is because in order for a population to just continuously exponentially grow, there needs to be enough like space for the new offsprings to live, and also there needs to be enough food, water, and other things for the population to continue growing in such a high trajectory. But we know that's not how it is in the real world, right? Like we usually reach a carrying capacity and things like that. So that's why we're gonna look at a different equation. So the first one is kind of in like an ideal world if you had like unlimited resources. But realistically, we're going to follow more of the second equation. And in this one, the K is going to be the carrying capacity. This essentially tells us how many number the like ecosystem can sustain over time. So it's a function of an environment. So in certain functions, the K might be high, in certain environments, the K might be low. So it's just the number of individuals that can be sustained. Okay, and then now we're going to look at what does a small n mean, or sorry, what does a small, yeah, what does a small n mean and what does a big N mean? So we're just going to go through different variables. Here they're asking what happens if n equals k. So in the equation, when the number for n equals k, that means the change in number or change in time is equal to 0. So it's essentially saying that there is no change in the population. The population is stable. The rate of people coming into the population is equal to the rate of the individuals leaving the population. be careful not to assume that this means there is no new birth or no new death. It just means that the number of like people dying is equal to the number of people being born, or it means the number of people entering the population is the same as the number of people leaving the population. It just means it's stable, not that there's no like new individuals or old individuals leaving. All right, now we're going to be looking at the n value. So when n is really small, the population is growing exponentially. So it's essentially saying like the actual number of new individual added is like very small, but because n is small, so as n nears the value, say like like half of k, then that means the change is approaching its maximum, and as n approaches k, it's going to decrease. So another way to make sense of that is when, let's see, when n is going closer and closer to k, that is that they're like like n is trying to be the same number as k, then the change in the population is smaller. Okay. So what assumptions are made about this development is, so first off, I don't think we talked about this, but this is called the logistic model. And it kind of looks like this. And then this is where our carrying capacity would be. So in this model, we're assuming that resources in space are limited and they limit the growth of the population. And we also make the assumption that these factors are going to determine how many maximum number of individuals can be sustained over time. All right, now we're going to look at an example. So you and your friend have monitored two populations of wild lupine for one entire growing season. By carefully mapping, tagging, and censusing the plants throughout the period, you obtain the data listed below. Calculate the following parameters. So here we're gonna actually, let's come back to this since I have more questions. Okay. All right, let's come back to this. And then let's look at 5. So we're looking at the exponential growth formula, and we're trying to determine the amount of time it takes for a population to double in its size. So it's saying we know R max or R, and the doubling time is equal to log 10 of 2 over log base 10 of 1 plus R. So we're going to be using this formula and trying to answer the following questions. So it's saying if the population of a country is growing at 2% per year, how many years will it take for the population to double? So for this, we know that we have 70% already, like given in the question. They're saying that the doubling time is 70 over R. And in this question, they tell us that R is 2%. So which means R per year is going to be 35 years. So doubling time equals 70% over R. And we know R is given right here. So that's 2%, and our doubling time is going to be 35 years. All right, and then the next one, they're saying it's only 1% per year, so same equation. But we're going to replace the R with 1%, which means our answer is also going to be 70 years. Does that make sense so far? All right. Thank you for the answers. Okay, so next we're going to be looking at a different question, and we're looking at, let's see, different strains of bacteria. And we will begin with a tiny colony on a petri dish. One day later, we see the colony grew and exactly doubled in size. So they're telling us that it's doubling in size in one day. And then we're also calculating to show that it continued to grow at the same rate, so it has a constant rate. And we did this over 30 days. So we're assuming that it happened for 30 days. And now we're trying to find R value and like how long it would take for half of the petri dish to be covered. So for the first question, it is asking what is the value of R? And from question 4, if you know R, then we also know the doubling rate. So they gave us the equation up here. We can use this because that has R in it. So we can do log base 10 to divided by log base 10 plus 1 plus R. And then the value can be estimated, and we know that there's 70%. So from part B of 5, we took 70 and divided by the percent it increased over time. So again, we can assume that 70% over R equals 1 day. And we know that this is 1 day because in the question they said a day later it doubled exactly in half. So we know 70 over R, whatever this is, needs to be, the R needs to be something that gives us 1. So the only answer that can be is 70. So R equals 70 because 70 over 70 should equal 1 day. So we can go this way or we can do it this way. So this requires a calculator, but if you didn't have one, this is a good way to estimate it. Okay, and then the next question is asking on what day would the bacteria cover half the plate? So they told us that the bacteria doubles in size every day and completely covers the plate by 30 day. So using that logic, we know that on 29th day, it's half the plate. Because on half the plate, if that half the plate doubled again, then that would give us the whole plate. So the doubling only happens for the cup when it's covered in half to give us the full. So another way to think about it is if you have this and it's covered, and this is going to be on the 29th day. And question tells us that colony doubles every day. So if we double that 29th Petri dish day, we're going to get exactly a whole plate. And this is going to be 30th day. All right, so for the next one, we're going to collect, or it's saying that we collected data on birth and mortality in 3 populations of grasshoppers. And we're going to calculate the birth and the death rate of the population. And it's also telling us that both the populations are experiencing an exponential growth. So first, we're going to be looking at true or false statements. So this one is saying population A is growing at the fastest rate. And this one would be false because we can tell that the birth rate and the death rate is almost like 10 off in population A and similar to B, but C, we have a lot more birth than we have a lot more death. So the most growing population is not A, just because there's also a lot of death rates. And the next one is saying population C has the lowest death rate, and that would be true because it's 0.05 compared to 0.35 or 0.8. All right, what do you guys think about the next question? It's saying population C is at the slowest rate. Is that true or is it false? Okay, like I mentioned for A, population C is the one that has a lot more birth rates than death rate. So it's actually experiencing a faster rate, which makes this false. And then the next one is saying that all population are growing at the same rate. And for that, we can do 0.9 over 0.80, 0.45 over 0.35, 0.15 over 0.05. And if all these numbers equal the same, then we know they're growing at the same rate. And if you do that, you do get the same number. So this is true for that. Even though these are much smaller numbers, the proportion is the same as the proportion for B and the proportion for A. But looking individually, like for example, like that's why we said population C has the lowest death rate. So looking individually, population C does have the lowest death rate, but it also has the slowest birth rate. So we kind of have to know when to apply proportions and then know when to look at an individual slot. All right, and then the next one it's asking which year was the birth rate greatest? So it's telling us in a herd of bison the number of calves born in 1992, 1993, and 1994 was 55, 80, and 70. And it's asking when was the birth rate the greatest? So it might be tempting to say that it's 1993 because we have 80, but we need to keep in mind that in order for us to determine rate, we need years. So you can only say how fast something's happening if we know like the year and the like whole population size. So we cannot answer this question because we don't know the population size. And the number they gave us, 55, 80, and 70, those are just the number that were born. But because we don't know the population size or how many were in there to begin with, it's really not possible to answer this question. Okay, next question says a population of pigeons on west side of the town has a per capita annual growth rate of 0.07. A separate population of pigeon on the east side of the town has a per capita annual growth rate of 0.10. If the populations both grow exponentially, oops, okay, there we go, and our census the following year, in which population will the change in number over the change in time will be the greatest? So this is again a trick question because we cannot answer it without knowing how large the population was initially. So if the population was the same for both of them, then we can say it will be greatest on the east side, but because we don't know what they began with, it's really hard for us to tell. Okay, and another example, again, we have a lot of graphs here. So here it's saying mortality rate is around 30%. So if we have 100 population, then we know this is going to be 30. This is 6 because it's saying 100% of the population is going to die. So if the number of deaths was 6, then the survivors are also going to be, like, we're going to begin with 6. And then for this one, it's going to be 0.50 because number of survivors 60, number of death is 30, so 60 divided by 2 is 30, so half is our mortality rate. All right, so we did filling the missing part, and the next part is saying, owing to a good food supply and small predator population, the rabbit population is growing by leaps and bounds. The rabbit called a meeting to discuss population control measures. 2 strategies are proposed. Delay all rabbit marriages until age class 2 to 3, and then it's giving us the assumptions that rabbit never breed until after marriage. And then the other one is saying sterile all rabbits in ages 3 to 4. And then it's asking us which of the following proposed strategies will be more effective in slowing the population down. So if we go back here, so for this one, it's saying sterilize them, this population. And then another proposed one is wait till marriage. Or more specifically, it's saying delay marriage. So for this, in the first 2 years of their lives, each producing pairs will have an average of 1.5. So it's saying delay this to this. So we see it's going from 1.5 to 2.0. So for a cohort of 100 rabbits born in years 0 to 5, 90 or 45 pairs will each have 1.5 offspring. And during years 1 to 2, they will add about 67 rabbits to the population. And when the cohort reaches age class 3 to 4, it'll consist of 30 rabbits and 15 pairs. And each of the population will have an average of 2.5. And that's going to result in 35.7 rabbits. So just looking at this number, we know the more effective one is going to be to limit by delaying marriages until 2 to 3, because if you sterilize all rabbits in class age 3 to 4, then we already have 1.5 and 2 offspring per producing pair, and there's more producing pairs for that. So the most effective way to do that would be to delay the age. So I'm just going to write that down here. Any questions on that? I know that was a lot of words and numbers, so let me know if that didn't make sense. All right, let's move on to the second part of this worksheet. So it's logistic population growth and fisheries. So I'm not sure if we're going to be able to get through all of this. We might be able to, but I know there's a lot of numbers, so it might be hard to follow if you don't have the worksheet with you. So I'll try my best to make it as clear as possible. So the first part is saying, suppose you have a farm on which you grow, harvest, and sell edible freshwater fish. The growth of the fish population is logistic. So it's already telling us which model we need to be using. And then it's saying we want maximum yield. So we want maximum rate of production for your own farm over a number of years. As a fisheries manager, you're responsible for deciding how many walleye can be harvested without destabling the population. So it's essentially saying like we want the most amount of population, and then we want to be able to take the most amount of populations out of it to harvest it without causing like a collapse, without causing like a huge decline that we can't recover from. So let's see, let's look at the data. So they're giving us time in weeks, 1 to 12 weeks, and then they're giving us the population size, and we're we're going, yeah, all the way to 24. So 24 weeks, and we see the population. So when we first graph it, we get this nice logarithmic graph, and we kind of see it stabilizing around here. So question B, part B is asking how large should you let the population get before you harvest? Identify points on your graph and explain why this is the best size for the harvest. So we know that the rate of the production is the fastest at the point on the curve where the slope is the steepest. So that would be around C. So this is going to be the steepest part. So at that rate, our rate and change is increasing greatly. So we're producing a lot of individuals in that population. So when the population size n is very small, then the k value, so k minus n divided by k, this whole part of the equation will get large. But there are so few individuals in the population that the gain number is also relatively small. So the rate of the population growth is maximum when n equals 1/2 k. So just if like what I'm saying is confusing, just remember that the rate of the population is the maximum when n equals 1/2 of k. And another way to translate this is we know n is the number of, I don't want to say people, but like number of individuals in a population. And it's saying that the number of individuals in a population is the greatest when we are 1/2 at carrying capacity. Remember that K is carrying capacity. So using this logic, we know that carrying capacity is around E, and so it's around here, and 225. And if we take half of that, it's going to be around here. So we know this is where we're going to have the best size for the harvest because we're going to have the most amount of individuals and the higher rate. Does that make sense so far? I know these are really like difficult concepts to follow through, especially when there's like a lot of numbers given in the worksheet. All right, I'm gonna move on. So next, it's saying assuming carrying capacity of the pond is 250 individuals. Check your answer in part B by using the data in the chart and computing the changes in population size, delta n over delta t, when the population is at several different levels. So for this one, what you need to do is for every question, you need to go back to the population size and the time. So the first part was asking, it was essentially asking this, k minus n over k. So k is the population size. So first part says 25. So 25 too low. So we know that's definitely going to be around here. So we can say 25. And for the time, we need to look at the x-axis here. So using the population size and the time, we can use k minus n over k to calculate all these values. And if we do that, the first one is going to be 0.1. And then we can do the same, so change in n over change in t. So for that, we just need to use the carrying capacity values that they gave us to see what the rate is actually like. So for this one, it would be 0.05. And if we continue that, I'm just going to give the values, and if you want to work it out, you can double check with the values that I'm about to give here. So the next one would be 0.8, and then this one would jump to 8, 12.5, 0.5, 0.2, and then when it reaches too high, it's 0, and that should make sense because we've hit the carrying capacity, and once we've hit the carrying capacity, we're not bringing any new individuals in, and the rate goes to 0 because we're at a flat, constant plateau. All right, and then the next part, we're going to try to see what happens when we remove one type of species from a population. So, a researcher collected data on an experiment she conducted on two desert islands. The islands were similar in size, climate, species, composition, and richness, and they were the same distance from the mainland. Originally, the same species of snake was present on both islands A and B. In her experiment, the researcher removed the species of snake from island A. For comparison, the species of snake was not removed in island B. So basically, this experiment is looking at what happens when you remove snake A or a species of snake from island A versus leaving it in. So island A is snake removed and island B is snake in. And here is the graph. So the number of species of B goes down and A kind of fluctuate and stays the same. So one of the question is asking us to come up with a hypothesis that explains why there is a different number of species on island A versus island B. So again, we see in island A, it kind of fluctuates, and B, it goes down drastically. One thing that came to my mind was because there is a drastic change on island B where it was taken, we can kind of hypothesize that the snake was acting as a keystone species on both islands. And when it was removed from island A, another predator dominated and drove many of the one to extinction. So that's something else that we can think of is so snake was acting as a keystone species, and when we removed it, another competitor or predator started dominating it. And when they dominate it, they tend to eat everything and kind of drive species to extinction. This is why keystone species are really important as they try to maintain the super intricate webs between different animals. So it's in an ecosystem, it's bad when you remove a native species, but it's especially bad when you remove a keystone species that has multiple connections. And sometimes it can even drive to extinction or collapsing of the ecosystem itself. Okay, and one way we can test that hypothesis, so the hypothesis stated in A, is we can try to reintroduce the snake in A and see if it recovers, or we can remove the snake from island B and see if it follows the same trend as island A. looks like the graph didn't upload here, but what the graph looked like was that it had time of months, and then it went from 1 to 22. And then what happened on the y-axis was it was number of species. And that went from 0 to 40. And let's see, and I'm going to draw this in different colors. So let's say B is in green, and then we have A in blue. So what happened to the population of A was that it went from 5 all the way to 35, and then for B, it started at 35 and then it gradually came down to 5. So this was the kind of graph that's supposed to be here, but it just didn't transfer over. But so here, this would be a possible. So okay, so in part B, we talked about how a possible design would be to remove snake from island B and then reintroduce an island A. So if our hypothesis were true, then we would notice a graph like the one that I just drew. This graph would prove our hypothesis because once we reintroduced the snakes, it started going up. We had a lot more species. And then once we took the snakes away from beet, it started declining, further showing that it acts as a keystone species. Okay, do you guys have any questions? I know it was a lot of math and a lot of numbers, and that it's really hard to follow if you don't have the worksheet next to you. So please let me know if you have any questions. I will also put the extra credit sheet in the chat. Make sure to fill it out so you can get extra credit for showing up today. I'm glad it makes sense. Yeah, and thank you for interacting through the chat and like saying yes or no for like when you got it. That was really helpful. Thank you. All right, everyone, I'm gonna end the live stream in a couple seconds. Make sure you click the link so you can fill it out.